Wait for it. Give it a second. I believe. Hello, Lauren. And Safa. And Afra. And Herman. The whole crew's here. What's up, people?
What's up?
Hey, let me ask, are you guys in a waiting room right now waiting for me?
Yeah.
Interesting. That's not supposed to happen. Are you guys just supposed to join and you can have your own conversation until I get here? They're like, oh, the teacher's here, be quiet. Like I want to be that in-person experience. I want you guys to have inside jokes about me. I want you guys to be able to talk about me behind my back without having to use Slack or Discord or whatever. Whatever the hell kids are using these days. How's everyone's weekend?
Mine was chill.
Good. It's fine.
Staff was chilling. Herman was fine. Yeah. No one had an exceptional weekend.
I mean, the Lakers and the Heat game, those are kind of nice to watch.
I didn't even see those. Oh, but people saw that Virginia Tech game, right? Virginia Tech football stuff?
I like the NFL. I watched the Washington football team game, but not the Virginia Tech.
I'm sorry, Steph. I wasn't aware that you went to the Washington football school university.
I like the NFL better. Just my preference, and plus fantasy makes it like way more fun.
Stop it. This isn't about what you like. Okay. Your university needs your support. Okay.
You're right. You're right.
You better at least watch that UVA game, Safa.
No, for sure. I mean, I bought season tickets for this semester, but then COVID, so I got those refunded.
Yeah, that didn't quite work out, did it?
Yeah.
The stadium was empty. That was weird. I mean, it was good, but weird.
Yeah, all the fake noise is weird. At least like for the NFL, and yeah, it's all weird.
Well, if no one has anything else other than just reminiscing over back when there used to be actual noise, then we can get started on Discrete Math. Welcome back, everybody. Welcome to Discrete Math. That's our small talk for the day. More small talk after class. But right now, we have to talk about section 4.1, which is what we started last time and what I've been hyping up for like weeks and weeks and weeks and weeks and weeks and weeks and weeks now. And the reason is section 4.1 is where we actually start proving things. So if we go over it, if we go over it, really everything we've done so far has just kind of been us building a foundation for us to talk about how to prove actual mathematical things. I mean, so far, let's talk about what we've had. We've had statements, right? And those kind of came from just, we kind of assumed things can be true or false, right? So when we talk about statements, statements are only things that we assume to be true or false. And we kind of make this assumption that everything is either true or it's false. It seems like a really basic assumption, but it's an assumption. Some people don't make that assumption. There's whole branches of math of people spending their entire careers doing things where they don't make that assumption, because we've ran out of ideas in math apparently. But yeah, so that was an assumption, right? And then we had our logical operations, right? Like and, or, not, XOR, implies, biconditional, all of those 16 possible ones, right? And all of those are just defined. Right, we just defined like what those what those were with truth tables, right? And those just came from statements. So we have made our assumption of statements existing, and then from that we naturally had logical operations. And then we had our logical laws. And those were just proven. proven from operations. So like logical laws, it's really nothing to new. We just prove those work based on the definition of those operations, the definitions of operations, or based on truth tables coming from statements, right? And after logical laws, we had predicates, which were once again defined from statements. We used to define it to be that thing where if you plug something in, it becomes a statement. And then the last thing we did was quantifiers. Fraud, there exists, that kind of thing. And all of those, and these were another kind of assume to work the way we think is what I'm writing. The way we think. If you remember that random lecture on for all and there exist statements, or for all and there exist statements being kind of related, the yin and yang property with like and or. For finite cases, we could define them in terms of and or. For infinite cases, we had to assume they work the way we think, meaning that for all just means everything in the set, even if it's infinite, and there exists just means one thing in the set, even if it's finite, and then they're the opposites of each other, even in the infinite case. The point is, oh, and I forgot arguments. I should go in here somewhere. And these are proven from truth tables. Proven from definition of operations. So really, this whole time, everything we've been doing has just been building up all of these different things, which really kind of all come from the assumption that things are true or false, and the assumption that for all and there exists to work the way we think it does. That's it. We've made two or three, depending on your count, very basic assumptions, and we've been able to build all of this logical speak, right? And now that we have this logical speak built, we can actually start to prove really cool, interesting things. So, any questions on this? This is like our meta-analysis of logic right now. This is just me kind of recapping what we've done so far. So that you guys know that, I mean, we are really building this from scratch. This is what we have. So, one more thing to note before we get started today. And that is arguments work with predicates. And by that, what I mean is like for statements, you know, we have that P and Q, we can therefore conclude P by specialization, right? This also works for predicates. So if we have that P of X and Q of X, we know that for all X in a domain, P of X and Q of X, well, we can therefore conclude P of X by specialization. So what I mean by that is for all X in a domain, if you can prove that P of X and Q of X is true, then you can conclude, or if you know P of X and Q of X is true, then you can conclude that P of X is true. But modus ponens, this all works here. Is that kind of making sense? I hope that makes sense. It makes sense once we do some examples. But like let's say we're given example, given that for all X in the real numbers, right? If X positive then X is greater than 0, right? Then what you can do, right, is like you're trying to prove claim your claim is 2 is positive, or claim is that, I'm sorry, wait, let's do the other way around. If X is greater than 0, then X is positive. So if your claim is 2 is positive, your proof can just go like this, right? By given, 2 is greater than 0 implies 2 is positive, since 2 is greater than 0, by modus ponens, two is positive. And so all we have here is we're saying that this implication, this if then, works for all X, right? And we're kind of applying it to our specific case here. And it goes like that. This is more confusing than I meant it to be. And honestly, we're kind of gonna skip the modus ponens part. I just want you guys to know there's arguments happening under the hood here. So the point is, don't remember this too much. Just remember from this that there are arguments happening under the hood. We haven't abandoned arguments, right? They're still happening. We're just not making them as prominent anymore because now we're moving on to bigger and better things. Any questions? Good. So the bigger and better things are direct proofs. And before we start proving things, we need to have things to prove things about, right? We need to have subjects that we're proving things on. So that sounds weird. Not human subjects. We're talking about mathematical subjects. And so what I'm talking about here is, let's get some background info. And first, let's talk about important sets. All right. So remember, sets are just collections of things, and some very important sets are the following. So we have the natural numbers, I'll say for the natural numbers, which we give this cool looking N symbol with like a bolded one line there. And what that equals is that's just all your counting numbers. So that's 1, 2, 3, 4, 5, ... So I'll say these are counting numbers. Makes sense. You guys probably heard some of this before. And then we have the integers, which we read as a Z with a cool looking thing like that. And these are the counting numbers, 0, and the negative counting numbers, all kind of like these whole numbers, positive and negative. And so that could be like -3, -2, -1, 0, 1, 2, 3. It goes on and on and on in that direction. So these are all the counting numbers and 0 and all the negative counting numbers, right? And we should all kind of have a grasp what the integers mean and what they are. And the integers are really our starting point for this entire class. I kind of said earlier, I think, in one of my lectures that everything needs to come from some kind of starting point. The integers are our starting point. And so we may assume we know how these work. Specifically, so specifically, we can make the assumptions. We are allowed to eyeball if a number is an integer. Or I guess more formally, I could say you're allowed to identify a number as an integer. And by allowed, all I mean is that if you're doing a proof, right? If you're doing a proof and you get down to x equals 2, you can go, okay, 2 is an integer. You know 2 is an integer. You don't have to prove beyond that 2 is an integer. And we'll talk later about things that you will have to prove, right? So the point is you're allowed to identify numbers as integers. That's fine. You can use that the integers are closed under addition. And what does the integers being closed under addition mean? First of all, what does that sound like it means to someone that's never heard it before? Does it sound like no shirt, no shoes, no service? Like, does it sound like they don't work? So the integers are very open to addition, but what it means is that closed under addition, which means that they're open to the concept, but they're closed under it, which means for all a and for all a and z and for all b in the integers, a plus b is in the integers. All I'm saying is if you add any two integers, you're going to get an integer. So it's closed under addition, what that concept kind of means is that you can't get out of the integers just by adding two integers together. Now you can also assume that n is closed, I should say is here, because even though there's infinitely many natural numbers, the set itself is just one thing. I'm saying the set is closed. So n is closed under multiplication. So for all a and z, and for all b and z, a times b is in z. Same concept, right? You multiply a into integers, you're going to get another integer. So here's a question. Is n closed under division? What do we got? Lauren says no. Why do you say no, Lauren?
Because can't you divide two of them and get like a really long decimal?
Exactly,
Or
right?
any decimal?
Yeah, it doesn't have to be a long decimal, right? Example, 1 divided by 2 equals 0.5, which is not an integer. And remember, we're allowed to identify integers, right? So we kind of just proved that. Oh, you guys can see that. All right. And then the other thing you're kind of allowed to assume is Actually, this is good. This is it. This is it. So, the integers are our starting point, and these are the things we're allowed to assume about them. Literally, basically, everything else in this class, we will prove to be true. So, no more assumptions anymore, right? We're no longer relying on our intuition or relying on anything. We're basically just relying on what we have right here, what I've written down right here are facts, and relying on our logic that we have, the logic we built our foundation on the last like 4 or 5 weeks or whatever, and algebra. You're allowed to assume how algebra works. Like you're allowed to assume that like if, and I'll also say in general, can assume you know how algebra works. So for example, if you know x plus 2 equals 5, then you're allowed to do that implies that x equals 5 minus 2. You can subtract 2 from both sides to get that x equals 3. Right? You can do algebra like that, or you can do something like how x plus 1 is greater than x, that kind of thing. But other than natural numbers, logic, the things you know about the natural numbers, or sorry, integers, logic, the things you know about the integers, and algebra, other than that, everything's going to be defined and proven from the ground up. Who's excited? I mean, come on, this isn't that much, right? We're not really assuming that much, and actual math assumes a lot less than this. Like actual math like starts down here. We're starting like right here. So we're starting a little above actual math. Like actual like formal mathematical logic derivations, all that kind of stuff. But the point is the things you do with this, like all this goes down, that goes down, 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 and we're gonna go all the way up like 30,000 stories to get to modern math. Okay, so let's get started. Let's start climbing. So let's first define some more important sets. So Q is going to be the set of all things that looks like A divided by B, such that A is in Z and B is in Z, and B does not equal 0. Other way to put this is just all fractions. Why is this important?
If b is 0, then it's going to be invalid.
Yeah, you can't divide by 0, right? You're going to get something that's undefined. And we can talk about that later, but dividing by 0 literally means undefined. It just means we don't have a definition for what it means. And I hope you guys are starting to get some more context for what undefined means, because literally everything else is defined. This is the, I'll put little things here. This is the definition of the rational numbers. This is defined from the integers. And you have to use like things like ands, right? Our logic operations come back. So it kind of uses everything. All right, the real numbers. You don't have to know this, but I think for some of you that have taken calculus, it's interesting. The real numbers are literally defined as being the limit as n goes to infinity of x subscript n, such that for all n in the natural numbers, xn is in the fractions. So what this means is that the real numbers are the set of everything that's a limit of rational numbers. So any sequence you can make with rational numbers, oh, I should call these are rationals, by the way. These are the rational numbers, and these are the real numbers. Good. So, yeah, so rational numbers are just fractions between integers. Real numbers are limits of rational numbers. You don't need to know that. This is just some high-level technique stuff. What real numbers really are, the thing that you can think of it as, is all numbers on number line. That's all they are, right? And no real gaps. For example, you know, you have 0, 1, -1, 2, 3, 4, -2, -3, all that, right? If we just took the fractions, well, we'd be missing like pi, for example, which isn't a fraction, but it's on the number line. So the real number is all the numbers on the number line. So the irrational numbers, we don't have a symbol for. We actually just write them as R, and then we do this \Q. And what do you think that means right there? Come on, who's got me? How would you describe an irrational number? I'm getting the sensation that a lot of you are thinking, I wouldn't describe irrational numbers. I would never dare. But if you had to.
B with the limit, B multiplication the limit and divided by A, if we put it like that.
Oh. I was gonna write I was gonna say it a lot simpler offer, but you could do something like that. I was gonna say that irrational numbers are just real numbers that aren't rational. That's it, right? I mean, irrational numbers, you might think of them as decimals that like go on forever and never repeat, that kind of thing. But decimals that either stop, so decimals that terminate or repeat, that's exactly what the rational numbers are. So the irrational numbers are just everything that's not a rational number. So these are just all non-rational real numbers, like the square root of 2, pi, e, etc. All right, any questions in this background info? I think this is also we heard before, is maybe put in a more formal context. The point is, though, right now, we don't really know anything about the rational numbers and the real numbers other than these kind of definitions. Everything else about them we are going to prove, which is awesome. So, first things first, though, we have more definitions. So they're important sets. Now let's do definitions. Definitions. All right. So this is going to be our definition of even numbers. So for all n and z, n is even if and only if there exists a k and z such that n equals 2k. And by the way, this is exactly how all definitions are, right? Like we have the thing we want, it is even, the thing we want to define with a biconditional, and then we say how it's defined. Hope that makes sense. And all this is saying is that evens are multiples of 2. Are multiples of 2. Right? Because this is saying for every natural number, or sorry, for every integer n is even if and only if for some other integer k and z, n equals 2 times that k. So if n equals 2 times an integer, that means, well, n's a multiple of 2. So it's just saying n being even means n is a multiple of 2. Make sense? Now odd numbers are interesting. For all n and z, n is odd. So this is the definition of odd, if and only if there exists a k in z such that n equals 2k plus 1. So this just says odds are evens plus 1, basically. Are off from evens by 1. Which should make sense based on our intuition how these things work. Any questions on this? Okay. Now we're going to define what it means for one number to divide another number. This is going to be the divide symbol. So for all a and z, and for all b and z, we say a divides, no, not like that. We say a divides b like that with a vertical bar. So this means the way you'd say it is a divides b. And what do you guys think? How would you define this notion of a divides b? Like, for example, we say 3 divides 6. Why does 3 divide 6?
Because it goes into 6 twice. Is that right?
Yeah, because it goes into 6. Because it goes into 6 a whole number amount of times, or an integer number of times, right? So 3 divides 6 since there exists an integer 2 such that 6 equals 2 times 3, right? Meaning 3 goes into 6 an integer number of times. And that's exactly how we're gonna make this definition. A divides B, we say that A divides B if there exists some integer k such that B equals AK. I should write a KA, I don't know why. Doesn't matter. So all this is saying is that A divides B if we can find an integer such that B equals A times K, A times that integer, right? Meaning, by the way, so all this says is that A divides B if B is a multiple of A, right? Any questions on that? Good. That's important. That will come up. Now we can divide prime. This was cool. for all P and Z, we say that P is prime if and only if P is greater than 1 and, this is going to look weird, P is greater than 1 and for all Q Q divides P implies Q equals 1 or Q equals P. All right. This is the really mathy way to write this. Can someone translate this for me? What is this actually saying here?
P is prime if it's only divisible by itself in 1.
Exactly. P is prime if it's bigger than 1 and it's divisible by itself in 1 only, right? This part right here is saying that if Q is a divisor of P, it must be itself or 1, meaning all divisors of Q are itself or 1. So this means P is prime if greater than 1 and its only divisors are itself and 1. And these, are, by the way, are called trivial divisors. Just because duh, obviously, any number divides itself. 1 divides any number. So it's trivial. All right. Last definition. Then we can actually go with the proof. So composite. That just means the opposite of prime. And so we can say for all N and Z, N is composite if and only if we have the opposite of N is prime, right? N's not prime. But N not being prime, a way we can write that, actually let's keep it like this. But what's this mean? This means for all N and Z, N composite, if and only if, like if we kind of negate this definition of prime here, what we get is that P is less than or equal to 1, or there exists a Q, these should be in the integers, by the way. There exists a Q in the integers such that Q divides P and Q does not equal 1 and Q does not equal P. And this right here is literally just the negation of this, right? Like we flipped the P greater, like the opposite of P greater than 1 is P less than or equal to 1. The and flips to the or by De Morgan's law, right? And then once we negate this, the for all attention there exists. And then the opposite of if hypothesis, then conclusion is hypothesis and not conclusion, right? So we're saying there does exist some integer that divides P that's not 1, it's not itself. So there does exist some non-trivial divisor. All this means is that P is composite, if P is less than or equal to 1, or P has a non-trivial divisor. All right.
Professor, quick question.
Yeah.
Trivial divisor as in like very specific, right?
A trivial divisor, which up here I mean to mean itself or 1. So the trivial divisors. So trivial divisor of like 5, for example, are 1 and 5. Right. So the trivial divisors. Oh, you guys can see that. The trivial divisors of anything are just itself and 1. The trivial divisors of 100 are 1 and 100. Trivial divisors of 314 are 1 and 314. Makes sense? They're really obvious ones. And so P is composite if P is less than or equal to 1, or P is a single non-obvious divisor. All right. Any questions? All right, this really is an exhausting definition day. Now we can actually have to prove some awesome stuff about some of this awesome stuff. That's all math is. It's just one giant feedback loop of awesome stuff leading to more awesome stuff. And I can't get enough. Let's just say math is a in all-you-can-eat buffet of awesome stuff. And I haven't left the restaurant in 7 years. So let's start proving things. Let's actually start proving things. And one last thing. I talked about this last time, but I want to talk about it again. To prove things about an infinite set, or maybe I'll say to prove universal statements, so for all statements, on an infinite domain, let's call it D. How do we normally prove universal statements? With method of exhaustion, right? But that's not going to work here, because method of exhaustion literally goes and checks every single option. But if your domain is infinite, you can't literally go and check every single option. You just don't have the time, right? So we have to get more clever. Instead, so for example, let's say we're trying to prove for all x and d, p of x, right? And d is an infinite thing. So instead of using method of exhaustion to prove the statement p of x is true for every x and d you plug in, instead of that, I'm going to write instead again. I know I already said instead, but it makes more sense to me. instead prove that the property of X being in D must lead to the property of P of X being true. So by this I mean, D is probably not a random set of things. Everything in D probably has something in common, right? There's some properties they share. And so if you're trying to prove something about infinitely many things, instead of using method of exhaustion to check each one, which would be exhausting, instead, all you have to do is show that the property that all the things in D share naturally must lead to the property of P of X being true. Because then if you show the property of something being in D leads to the property of P of X being true, that means that everything in D must satisfy P of X. This is the idea. We're going to do an example right now, which I hope helps you get the hang of it. Okay. It's a claim. Every square of an even number, actually it's getting a little weirder, of an odd number is odd. We're actually proving something now, people. This is what it's all about. We got to it. See, I feel like this is how math works. It's like at the beginning of class, we always say we're going to do something interesting today. And then we take you through so much boring crap. By the time you actually get to the interesting part, you forgot it's interesting. This is the interesting part. We're proving something. Okay, about an infinite set. So first of all, let's write it formally. All right? I mean, this is using some street lingo right here. Okay, this is some vernacular. How would you say this in formal math? First of all, is this a universal statement or an existential statement?
Universal.
Universal, right? So we're saying for all n, what's our domain?
Odd numbers.
Sure. In the odd numbers, which you could write, by the way, as 2k plus 1, as all numbers of the form 2k plus 1 such that k is in z, because we know that's what it means to be odd numbers. Other way. What are we saying about all these odd numbers?
This square is odd.
The square is odd. Exactly. And remember, because of how universal quantifiers and conditionals work, another way you can write this is that for all n and z, n odd implies n squared odd. Right, same thing. All right, let's prove something. All right. So once again, this should make sense to us, right? We start thinking, we go, okay, wait. 1 squared, 1 is odd, 1 squared is 1, that's odd. 3 is odd, 3 squared is 9. Yeah, that's odd. 5 is odd, 5 squared is 25 is odd. It seems that every odd squared is going to be odd, but why? Right? How would you prove it? How would you prove that's always true? Well, how about this? here's what I'm going to say. Let's start with this. Let's start with an arbitrary odd number, and then prove that that must be odd. Here's what I mean. Let n be an arbitrary but particular odd number. All this means, all this arbitrary but particular odd number business, all this means is that we don't know which odd number it is. Like, I'm not saying n equals 7. I'm not saying n equals 17 or n equals 35, right? I'm just saying we know n is odd. N is a number with the property of being odd, right? But it is a particular number. We can't just keep switching around and being like, okay, let's make n equal 3 now, let's make n equal 5. It is a, like n right now is one number that is odd. We just don't know what number it is. We have to work with that. Cool. So what do we know about n if it's an odd number? We only know really one thing about it. What's our definition of odd?
If it's a multiple of 2 plus 1.
It's a multiple of 2 plus 1. You can write it like 2k plus 1. So I'll say, by definition of odd, there exists a k in the integers such that n equals 2k plus 1. That's just by definition of odd. It means we can find this k. Right? Now I'm going to say, let's consider n squared. N squared equals 2k plus 1 squared by substitution, right? We're just substituting 2k plus 1 into here. And then 2k plus 1 squared, that equals 2k plus 1 plus 2k plus 1 by definition of exponentiation. And then what can we do with this?
Expand or distribute.
Yeah, we can distribute FOIL that whole thing. This is going to be 4k squared. We multiply that, and then we're going to have, what's that? 2k plus 2k plus 1 by distribution, right? Which is 4 squared plus 4k plus 1 by addition. Does this number look odd to anybody? What's it mean to be odd? It means that you're a multiple of 2 plus 1. Well, heck, this is something plus 1. Is this a multiple of 2? So plus 1 does not necessarily mean odd, right? For example, 6 equals 5 plus 1. but 6 is not odd, right? Even plus 1. It has to be an even plus 1, and even is just a multiple of 2. Does this look like a multiple of 2? Hell yeah, right? This can be written 2 times 2k squared plus 2k plus 1 by factoring, right? Does this make sense? And what is 2k squared plus 2k? Well, remember, k is an integer, right? And 2 is an integer. Meaning, since the integers are closed under multiplication and closed under addition, this whole thing right here is another integer. So this can be written as 2 times some integer plus 1 by factoring. Thus, or say note, since 2 and k are integers, and the integers are closed under addition and multiplication, right? 2k squared plus 2k is in Z. So we're being closed under multiplication and addition. That just means any two integers you multiply, any two integers you add are going to also be integers in the result. And so the result of k squared is going to be integer. The result of 2 times k squared is an integer. The result of 2k is an integer. And so the result of 2k squared plus 2k is an integer. Thus, since n squared equals 2 times 2k squared plus 2k plus 1, and 2k squared plus, I'm sorry, we don't want that. It's this parentheses then plus 1. And 2k squared plus 2 is an integer. N squared is odd by definition. Can someone put words in my mouth while I'll mouth them and you talk? Okay, no, this is amazing. I'll do it, right? I'll raise my hand. This is amazing, right? We just proved beyond any doubt that every square of an odd number is odd. This did not require any assumption, right? This didn't require us to go to check all the infinitely many odd numbers, which, by the way, 2C on written assignment 5 might have given you guys some trouble. And 2C on written assignment 5 said that 2 to the m minus 1 is prime. And it wanted you to prove it or disprove it. Right? This might give you guys, or where n is prime. This might be giving you guys some trouble because if you check the first few primes, 2 cubed minus 1 is prime. 2 to the 5th minus 1 is prime. 2 to the 7 minus 1 is prime. It takes until you get to 2 to the 11 minus 1 to get that it's prime. The point is, if you just check 3 examples, you'll get the wrong idea. That's not true. And in fact, there's some mathematical things that will actually hold and look like they're true until you get to like a millionth example, right? The point is infinity is a lot bigger than 5. Infinity is a lot bigger than a million. It's a lot bigger than a billion, right? It's impossible for us to check if infinite things work. We have to be more clever. And this is the more clever way. I mean, right here, all we did is we said that the property, right, of a number being even is that it can be written 2k plus 1 for some integer k. And then once you have that, right, The property of a number looking like this is that you can square it and it'll look like this, which has the property of being 2 to the integer plus 1. The point is the property of a number being odd naturally leads to the property that that number squared is also odd. Right? And since this works for any old arbitrary n, this works for every odd number. So all odd numbers have the property that they're squared, they're odd. Any questions? Does this make sense? Really? Good. If this makes sense, the rest of the class will be a breeze. Because this is the main idea. Everything comes back to this. Okay, well, that's class. Don't have any questions. Game over, people. Or day over. The game is still very much afoot. And we'll continue it tomorrow. Good, good, good. This is good. Good, this all makes sense. And notice, by the way, all this detail that I'm using is necessary to get full credit on homeworks and tests. Yeah. I have nothing else to say. I'm excited. Good, good, good. All right, now that we got the background information and all that out of the way, next class, and from now on, it's just gonna be basically proof after proof after proof after proof. And proving a bunch of stuff, proving things true, proving things false.
All right.
Okay.
That's it.
Yeah.
Bye.
Are you saying bye?
Yeah.
Thanks, everyone. Thanks for coming. Alfred, thanks for coming.
Professor, I have a question.
Yeah.
I think you can hit the stop recording. It's
Oh,
just
yeah,
related to homework.